Welcome back. It's Friday, it's Bayes. Well, how much better does it get? How many of you have ever gone on vacation and read stats books on your vacation? Guilty. I do. Sorry, I'm just kidding. I do. Actually, I do. It is. It's true. But each person has to make their own choices. I'm that type of person. All right. Let's start off with some announcements. Let me make sure I can see my screen just fine. Okay. Homework 2 is due next week, as you know. Office hours next week is only be 1 hour, but you know how to find me otherwise. We have next Wednesday with GMAS, right? I think GMAS is next Wednesday. So we have a student group meeting for EMS at 3 p.m. And then again, coming up in the middle of October, you get a break from me. So if you are tired of me, first of all, I totally understand. You should ask Lisa how she feels about that. But second, I'm serious, just ask her. You can have a week off from me, okay? Okay. What do you remember from last time? It was intense, I know. The highs, the lows. I did a matrix product.
Oh yeah, there's like an easier way to write models so you don't have to compile the problem every time.
Yes, that's right. The goal, there's sort of two parts to it. Compiling for simple models, it takes a couple seconds, but it's not that bad, right? But the bigger picture is, I think, writing out all the parameters, writing out all of the prior probabilities, all of that takes a long time. It's even going to get worse. Remember, I keep talking about this, but psychometric models are linear models, just with lots of items. Every item effectively is a linear model. So if you thought about how many parameters there was for one response with one linear model, you can imagine how many we get with psychometric models and how long that would take if you were writing out all the parameters. So the way I'm teaching this is to sort of unpack the parts of it, each of the parameters as we go, and then we start building on top of itself. So right now we're sort of transitioning to the part where everything will be piled into matrices, and the reason for that is it's a little bit more efficient. It's a lot more efficient to write for it. Anybody have questions about things we covered last time that you want to recover? Okay, no questions. I like it. Well, I think I left off talking about the model itself. And go here. In just a moment, I'll have my slides. And we were model section. Right here. Does this remind you where we sort of left off last time? We have the old model syntax on the top. This is without matrices. We have the new model syntax on the bottom. That's with the matrices. And the key in thinking of this, there's sort of two different changes. Let's just take a look at this model I sort of left off here. Our outcome is y. It is still just a vector, right? But we say it's equal to, it follows a normal distribution. The mean of that normal distribution is the product x times beta. That's that matrix product. Now remember where x came from. The best R function you've never heard of. Model.matrix. Right? It is our model matrix, which sometimes gets called a design matrix or a predictor matrix. And beta is the set of a vector of parameters that makes the matrix multiplication possible. Now, if you remember matrix multiplication from last time, you have to have the right size of the matrix to be able to pre- and post multiply them, right? In particular, our beta vector was, in this case, when we specify it in STAN, there were P coefficients, capital P coefficients, by one column. So P rows, one column. So that means whatever x is, x has to have P columns in it, right? The columns of the pre-multiplying matrix has to align with the row, the columns of the pre-multiplying matrix has to align with the rows of the post-multiplying matrix. So for instance, if I were to Yeah, let me just do some modeling real quick. Thump, thump, thump. It's coming. But if I were to go and misspecify this in Stan, guess what Stan's going to do? Stan, because it makes you specify all components of your model, if I went and said x was really 2 dimensions, like 2 columns instead of 6, Stan isn't going to like that very much. You go back to where I put 5. Matrices and contrast, where'd it go? Right here. So if I change this P right here to 2, and I go to build it, it should give me an error. Actually, it doesn't. Never mind. Okay, so it did give me an error, but it will give me an error if I submit data that don't conform to that, though. Yep, see, look at that. Had a problem. So it doesn't know to check the size of the matrices on input, but it certainly knows it when you when you compile the program, but it certainly knows it when you run it. So that was the key. That was the big change. So from now on, every time we build a Stan file, our goal is to try to use the matrices as much as possible. If you're using this in your own code and you're not familiar with matrices, that's fine. You can work on it yourself. Sometimes I don't myself. For really complicated models where I want to see everything written out, I won't use the matrices. It just takes a little bit more time to produce the code. But for us in class, we're going to try to build this more. It'll shorten our code. It'll make our life a little bit easier, particularly when we get to factor analysis, when we'll have, or item response theory, when we have a bunch of predictors, when we have a bunch of outcomes in our data. Any questions on the model part of Stan? Okay.
I have a question.
Yes.
I don't know if this is part of the models, but so when you do the matrix and then it gives you beta 1, beta 2, beta 3, beta 4, how is there a way where you can name?
No, that's one of the downsides. You have to remember which is which. But I'm going to talk about the guide as soon as I start running the model. Sort of how to know which is which, because it will come out. Turns out that model matrix that you submit as X, the names of the columns correspond to the betas that are in the parameter vector. Because each one of those columns is going to multiply a coefficient. So that's where you can grab those names from and know which is which as a guide. There may be a way, I just haven't looked into it. In Stan, Stan's pretty, well, better than most other Bayesian programs when it comes to user-friendly. But that is one of the downsides to it, naming things. Okay, other questions? All right, let's talk a little bit about the prior. Once again, we talked about beta. Beta is a multivariate normal prior. Remember, beta is a vector. It means there are 6 parameters in beta in this example. Actually, there are capital P parameters. So remember, the multivariate normal is like the univariate normal for multiple dimensions, multiple parameters, right? So it expects mean beta to be a vector as well. That mean is the mean of each of the priors for each parameter from before. So if I go back to our parameter section here, well, here we go. If you look at all of our parameters here, 1, 2, 3, 4, 5, 6, each of those occupies space and beta, right, in that order. So the mean beta is the mean of each one of these. So there's 6 zeros there. So to replicate the syntax above, we would put a vector of zeros. Technically in R, it's just an array of zeros. It's not a matrix, but an array. It's sort of the weird part. What R calls a matrix, it's not exactly what Stan expects when you put a vector in there. But so that's what it's done. Now, you remember the covariance matrix we talked about last time? It's correlation with scale, right? So it's size 6 by 6. The diagonal of that is the variance. So everything's a 1 standard deviation above. It'd be a 1 squared for the diagonal. And then the off diagonal is something that doesn't show up when we do each parameter by itself, which is the covariance between parameters. Now, one thing about this, just to remind you, the covariance of, let's say, x and y is equal to the correlation of x. Sorry, excuse me, I'm doing this backwards. My goodness. Sorry, everybody. Correlation, this is an R, correlation of x and y is equal to the covariance of x and y over the standard deviation of x times the standard deviation of y. So what does that mean? Covariance, if we do the algebra, is correlation times standard deviation x, standard deviation y. So that's what a covariance is. Covariance is not something we often think about, because covariance, when you multiply by standard deviations, does not range between 0 and 1, or negative 1 and 1 like a correlation does. So correlation, covariance. So what is the range of covariance? Well, it's units of x times units of y, first of all. It's sort of a unitful measure, whereas correlation does not have units attached to it. We sort of remove the units when we divide by the standard deviations. So covariance and correlation are very much tied together. You can always, if you know the standard deviations of each of the variables, you can always translate between covariance and correlation, back and forth. Or another way of putting that, if someone gives you a covariance matrix, the diagonal of that covariance matrix is the square of standard deviation. It's the variance. So you can always take a covariance matrix and turn it into correlation, because you have all the terms you need. So why I'm emphasizing this is I don't know of a case where you would want to pick a prior distribution that had a covariance between the parameters. First of all, you'd have to figure out the scale of the thing, which is impossible. And we talked about last time picking priors for regression coefficients. Remember the top, we had to think about what the scale of each was. We said the intercepts on the scale, units of y. Slopes are units of y per units of x, and those are really hard to figure out. Covariance is like that too. So I don't know that I'd ever see a case where you pick a prior where you think some of the parameters are correlated or have non-zero covariance, but it's possible. Any questions on that? Okay. So the top row right here is where we are defining the prior for beta. It is effectively when you have a 0 for the covariance, it's like specifying each prior separately. A 0 covariance in a multivariate normal distribution implies that each of the univariate normal distributions are independent. You may have taken a matrix algebra or a multivariate statistics class where you show that, derive that formulaically. I'm not going to do that for you, but it's true. In a multivariate normal, a 0 covariance is like saying each of the other priors are independent of each other, so it's convenient. So this is identical. When we specify this prior, if it aligns with each of the numbers that you show up in this old matrix right here, we have essentially specified the same prior for the coefficients, is what I'm going to. So what we're doing with this more compact syntax is not specifying anything differently. We're trying to recreate this model but with matrices. Any questions? Okay. So sigma, again, still follows that exponential distribution that we talked about originally. The only difference with this syntax is instead of specifying the prior value, I'll just input it as piece of data. And that's to allow us to just change the prior without having to recompile the code. Again, compiling the code doesn't waste a lot of time, but it's just to try to, if we're doing this for everything, just get in the habit of doing it makes sense. And again, when we get to psychometric models, remember, it's a lot more of this going on. So if you can easily automate the way of building priors, it makes it very easy to change values if you think that you're doing the wrong prior, or a prior that you don't think is doing the right way. Any questions? Okay. So, what are the summary of changes? The model is efficient. Models are equivalent, but with matrices there's less syntax, so right? The bigger problem is, as you mentioned previously, the output is not labeled with respect to parameters. Right there, you can see beta 1, 2, 3, 4, 5, 6. So you've got to sort of make sense of that. So let me do that real quick. Stan ran. Here's our summary. Okay, so you have our betas, 1 through 6. That is, what are they? So this is where, if you remember in your data, this model 05 predictor matrix, that is your guide. Because if you go and ask for the names of the columns, there's a call names function. These would be the labels in order of each of the parameters. So if you're writing to get output, this is actually, if you remember in the LM function in R, the output of LM, like the least squares version of this linear model, these are exactly the same labels that show up in that output. So when you create the model matrix with LM, with the model matrix function and that formula, R is attaching the label to each of the columns that it would display in output. So that's your guide to figuring out each beta. So 1 here, intercept, that's your intercept. Height 60 inches, that's beta 2, and so forth. How are we doing? Entertaining?
Can you say what you just said one more time?
I'll try. Thank you for asking. Thank you for giving me the chance. So in the output, if I showed you this, you'd be like, great, what's beta 1 mean, right? So that model matrix that you inputted has your guide. And the labels that are here would be the same labels if you ran this analysis in least squares for the output. So let me give another. Did that?
Yeah.
Let me just show that one more time real quick, because if I change this instead of formula, I type LM. There's those same labels: intercept, height, factor, so forth. All right, these are the least squares estimates. Whereas above here, those are just the same labels that came off from the matrix themselves. Okay?
If we use the non-compact version of the code, do the labels show up?
Yes.
Okay.
Yes. So whenever you specify a parameter, what shows up in the output is the name you specify. And if you specify a parameter as a vector or a matrix, then the output displays which element of that is shown. So in our previous output for model 4, these were the labels, although it's hard to see. Make this a little bigger here. These are the names of the parameters we specifically put in our syntax, so it shows up there. In the output, you just have to keep track of them. It's not easy, but it is, unfortunate. It's sort of like the penalty for the efficient code is having to remember or keep track of these things at the end, but it does start to make a difference. Now, other questions on this? There's one other part of this I really wanted to share. In building Stan, we could have defined our model where instead of having y, remember y is a vector. And when we say y by itself is normal, it's assuming that all the elements of y follow that normal distribution. The mean of each of those is x times beta. What we could have done alternatively is we could have specified y for each actual observation within a loop. We could have said for observation 1 to n, y tilde normal, and then we should specify the mean for each. This is something that's called vectorized code, right? It's taking what would happen in a loop and displaying it only as a vector. This is really fast code from the get-go. So when you find yourself in Stan, it's often the case, particularly when you get into psychometric models, you may want to write a loop somewhere. And you can, and it works the same. It just, when Stan compiles it, it runs slower. And I keep talking about running slower because you can imagine if we have a lot of these going on, it's going to start taking more time to do these analyses. So whenever possible in STAN, writing code that looks like this, where the outcome is not in a loop, is faster. And that term for that is called vectorized. It's a term that we use in computer or coding languages. The same thing happens in R, right? The for loop in R takes a long time to process. But if you can somehow make your thing in the loop into a function and call it with apply, it vectorizes what's happening with the apply function and it goes faster. So it's just a subtle thing. But since we're talking about efficiency in code, I wanted to bring that up here. I'm not doing much more than that. And the first rule of this class is the same as the first rule of anything. Make it work, number one. Make it better, number two. I bet some of you know what I'm talking about. How many of you have run a STAN code that took hours? Make it work, though. That was the make it work part. And then we make it better, right? So that's if it works and it's slow, that's better than it not working or working incorrectly and fast. Yes?
Can you explain to me how a vector would account for different distribution? Like, I know we're saying they're all normal,
Right.
but like, it's not clicking for me how the mean or sigma could be different for each.
So what's happening here when we have this matrix product, because we specified these terms as a matrix, it calculates it, and it knows that the result of this is the same length as the y. So it's like saying for each value of y, I have its mean. Now, because we specified sigma as not a vector, STAN was coded in such a way to say, if you have a vector over here and not a vector over there, replicate the part that's not a vector. So it just takes a copy of it and puts it down. So that's how it's functioning.
Okay, now I'm sorry.
No, please don't apologize. Please ask your question.
Great, it's a matrix product essentially that's happening.
Yes.
Beta is going to be the coefficients, and X is going to be your predictor matrix.
Correct.
Model matrix. Great, okay.
That's the question.
Clarification, yes.
Okay, gotcha.
I was making sure I was following.
Yeah, that's right. Beta is your coefficients. X is the model matrix that you designed from R elsewhere. So I wrote a Bayes package. It's called Blatant. I love it. I love the name. Here, let me show you. BLATENT. So if you know English, there's a word called blatant, right? And let me just define it. Sorry, this is my fun. Define blatant, totally offensive or conspicuous, obtrusive, or unpleasantly loud and noisy. I was going for that. But we were doing unpleasantly loud and noisy, Bayesian and latent variables. So I put latent with an E. You get it? Sorry, dad joke, right? Anyway, sorry. At some point, you just have to accept who you are. And I'm in that phase of my life where, look, I'm not a kid anymore. I still have some years left. I need to try to make the most of them. And so I'm just going to make it with puns, and blatant is that pun. But, I digress. Blatant runs on model matrices. You specify your latent variable model with a series of R syntax to formula, and it goes and it takes the model matrices and does the calculations for you. But it was because of that, it makes it easy. So where I'm going with this is that whole model matrix and putting things into vector is a really convenient way of doing a lot of what we do. And all of it is from linear models. So when people are like, I don't like linear models or whatever, I'm a psychometrician. Just remember, all of it runs on linear models in one way or another. Anyway. Okay, blatant. Yeah, I probably won't show you blatant in this class. It does Gibbs sampling. Anyway. All right, let me show you these results. Actually, I did the results. Other questions before we move on to the most interesting part of today? Any other questions on this? Online? No questions? Moving right along. Let's compute some functions of parameters. So, in Bayes, you know Bayes. Actually, yes, you do. Wanted to do this real quick. In Bayesian, you remember what we're doing in Bayes is we're calculating a whole bunch of posterior distributions, right? So for instance, if I wanted to look at the posterior distribution of 2, this is a model of 5 samples. There it is. There's our posterior distribution. Or if I really wanted to do this, I think if I take, oops, takes a little bit of time, but there's our betas, right? There's all of them. However, there comes times in life where you want to do something with these parameters. For instance, in your homework, you might want the slope for group 2. Right? We know that the slope for beta 2 is the height 60-inch slope on here. But it's a conditional main effect. It's a conditional slope, conditional on group being number 1. So how do we make the slope of group 2? A linear combination. And we do that because we have to figure out which other parameter we add to it to give us our slope. So in linear regression land, especially if you took like Lisa's intermediate class, you may have learned a package called GLHT in R to build these linear combinations, where basically it takes the value of this slope and it actually adds it to the value of that slope, and you get your new slope. And then there's something in the background with the standard errors and the covariance between them to give you the standard error slope. We need to do that process, but for Bayes. But here's the key. That new slope, because it comes from these two distributions, we could form a posterior distribution for that slope. In fact, we should form a posterior distribution for that slope. Because if all we're summarizing is, for instance, the mean of these, the EAP estimate, we will lose out on all the variability that we want to describe the certainty in our estimate. Follow me? So, let me go back to the presentation. If I stick to the slides, I stay on point. Just describe that. What are the types of things we would want to compute? Nising effects, which is the slope for group 2. If we had two continuous variables predicting or multiplying each other in an interaction, we might want to look at the slope of one conditional on the value of the other, or something called simple slopes analysis. We can do that too. If you're in a path analysis and you want a mediation effect or an indirect effect, it comes from the multiplication of slopes. Not the sum, but a multiplication. We can do that as well. Right? Or, also important, you may want your R squared. Turns out R squared, where do we get that from? There's several places, there's several formula that are equivalent, but each of them involves some type of predicted value. And that predicted value comes from our betas. So we could build a posterior distribution for it too. Yes?
In these cases, are we using the numbers from the posterior distribution, or are we computing these values at the same time with the betas and other prior distributions?
So yes to both.
Summaries and
If we do it well, so if we look at it this way, ideally each sample of the Markov chain, so each iteration that we're sampling and we're recording, has a set of parameters, a sample of this plot, right? Even though we pooled it into one. What we want to do is for every iteration then, is to compute the value we're interested in. Because if we take that across the chain, now we have sampled the posterior distribution. It's a function of these parameters as well. If we do only the summary statistics, if we only look at the mean, we'll get a point estimate of the mean. But when we look at the variation, it's not as simple as coming up with a formula to calculate the variation for it. In fact, we would want a shape for it. And there'll be some statistics, R squared being one of them, where if we calculate it for each sample of the chain, the shape of the distribution will certainly not be symmetric, at least for smaller samples. right? R squared is one of those. Anything indirect effect in mediation analyses is another, right? How many of you have learned about mediation effects before? A little bit? You remember there's a problem in calculating their standard errors or their p-values in a frequentist framework? And that problem is the mediation effect is a product of two values. Any one of those values, if you believe the assumptions of maximum likelihood, comes from a normal distribution, but the product of two normal distributions is not normal. So we have to come up with inventive ways to figure out what the distribution happens to be. In a Bayes analysis, we don't have to do that. We can just take the product at every step of the chain, and we have a posterior distribution that is not symmetric or not normal. It doesn't have to be that way. Does that help answer your question? Other questions? Okay. So the key in all of this, and I call this functions of parameters. There are some of the, I call them functions because I'm trying to use the term that's most generic. If you learned this GLHT package in R, it was something called a linear combination of parameters. Now a linear combination comes from a matrix product, but there's no squared terms in it. That would be a nonlinear transformation. R squared has a squared term in it. So a missing effect and a simple slope would be a linear combination, where R squared would be a nonlinear combination. So I'm calling the whole set of this functions of parameters. And here's the cool thing about it. When we have our Markov chain, there's two ways to do this. There's always two ways, right? There's the easy way and the hard way. When my kids were young, I always tell them that. There's the two ways to do things when we used to have a fight. There's the easy way and there's the hard way. And they'd be like, what's the easy way? So you just do it. What's the hard way? You do it and you fight me about it. Sounds bad, but it worked. It was effective. I'll take the easy way, my son. Like, wash your hands. Well, I don't want to wash my hands. Well, you got to wash your hands. You're going to make a mess. Okay. Long story short, the easy way is to get Stan to do this for us within the chain. The hard way is to take the chains that we already ran through Stan and compute it ourselves. And this is a nice feature of Stan itself. We can have it actually compute quantities that we want to have when we go forward. So this is fun. All right, so let's take an example. We need a slope for diet group 2. Remember, our linear model had a bunch of parameters. The slope for height, beta 1 here, is the slope when group 2 is 0 and group 3 is 0. Otherwise known as the slope for group 1. So what do we need to do to get the slope for group 2? Well, first, we have to figure out what the equation would be for that slope. What are the betas that go into that slope? So what I did was I took our model and I set group equal to 2. So when group is 2, we still have an intercept, we still have beta 1. Beta 2, or when group is 2, the group 2 variable, group 2 sub p equals 1. This thing right here. So this term, beta 2 multiplies the value of 1. Beta 3 turns out to be 0, not involved, because group 3 is equal to 0 there. Beta 4 times height shows up, because that's multiplying group 2. And then beta 5 gets destroyed as well, too, knocked out. So when we condition on group 2, this is our equation. Our regression equation. Turns out we can combine like terms. Right? If we have beta 1 plus beta 4 times height, that sum, beta 1 plus beta 4, turns out to be the slope for group 2. Ta-da. That's it. So what do we need to do to calculate the slope for group 2? Take the values of beta 1, add them to the values of beta 4, and there it is. Similarly, if we wanted the intercept for group 2, it's beta 0 plus beta 2. So it's a nice sum of parameters. So we could take, in our posterior samples, we could take our chain, we could highlight just beta 1, we could highlight just beta 4, and sum them together and get a value. Let me see if I can do that real quick. Yeah, right here. I actually did do that. So it turns out, let me go to my code here. So the slope for group 2, remember, we can take this is our posterior samples. This model 05 underscore samples is the object that contains all of our samples, right? $sign draws is a function that only highlights the draws or the samples from a specific parameter you tell it. So this is all of the draws for beta 2. We could form a new variable where we take beta 2 and add beta 4. And sure enough, there is the slope for group 2. Actually, this is incorrect because it should be beta 5.
Shouldn't it also be beta 3?
Oh, good question.
Because beta 1 in this case is our intercept.
That's right. So let's go back to, thank you for noting this. And this here is the label issue, right? So this would be, I should have relabeled my subscripts. This would be beta 1, this is beta 2, 3, 4, 5. So it's beta 2 plus beta 5 should be the result that we want. And I had it wrong in my, as you can tell, I've been doing this for a few years, probably longer than most of you, or some of you have been alive. And I got this wrong. So yeah, it's one of those things we pay attention to. I had it right, by the way, on my slide. I just forgot to fix it on my syntax. But beta 2 and beta 5, why did I know it was wrong? Because the slope shouldn't be 81. For 1 unit increase in height, your weight shouldn't go up 81 pounds. That's how I saw that wrong. So right here, beta 2, this is the posterior distribution. The mean is 2.08. So the slope for beta 2 is 2.08. And you would describe this just as you'd describe all the other parameters. In fact, you want to see the plot for it? It says beta 2 on it. It's not beta 2 here. This is the new slope for group 2. That's the posterior distribution. You can have a density of it as well, too. How's that look? Interesting? Yes.
So when you're adding beta 2 and beta 5, you're not adding the estimates for beta 2 and beta 5, you're adding the distribution.
We're adding the whole chain. That's right. So in fact, if I went and did the function MCMC trace, remember the trace plot, otherwise known as the caterpillar plot? This is the result for all of our iterations of the sum of those two parameters. So we literally have a chain now for that new parameter. Good question. Thank you. Other questions? This is cool, right?
This is like a matrix summation essentially, right?
We're getting there.
Okay.
This was the hard way. Pick your parameters, sum them at the end. The easy way is a matrix. It depends on your affinity for matrices, how much you like matrices. But
I might actually have to crack out my linear algebra textbook.
it's matrix products, though. We haven't done anything but a matrix product yet. There may be a matrix inverse lurking somewhere, but we're not there yet. But let me go to my slides real quick, because I have text on this. So you see that. So, turns out there's a section of SAN code, a brand new block of code in SAN called generated quantities, that will do this for us within the markup chain. So now I want to caution you, anything in generated quantities is computed after draws are sampled, right? So SAN is chugging along with the model that's specified in the model section of syntax. And at the end of that iteration, it looks for generated quantities and calculates them and then saves them in the object, the chain object, right, the trace. So if we put in generated quantities, if we define a real number, remember we have to define every variable in SAN and declare it, called slope G2. This is the non-matrix form. This is in the scalar syntax, right? And I sum the two quantities, beta height plus beta h, the two parameters, beta height plus beta h by G2. What it will do is calculate that at every step of the chain, every iteration, after sampling is done. And when you go and show the summary of it, sure enough, right here at the bottom, it shows up as if it were a parameter in your output, which is cool. right? So if you think about what you might need from a model, you add it to generated quantities, we can make this work. Why is this handy? Right? It sounds like we're doing this in linear models. Turns out there are quantities we generate in psychometrics when we get to psychometric models. One of the first ones we're going to generate, even though many of you know to not believe it and think it's a terrible idea, the coefficient alpha. I will show you how to build a posterior distribution for coefficient alpha. The confidence intervals around, or credible intervals around how much coefficient alpha should be for an exam. Now, coefficient alpha tells us very little, so we may not want to do it, but we could do it. And that's sort of the point of this. So, this is the syntax that I was just showing you here. Again, I'm back in scalar world. That should be 1,000 here. And don't take my word for it. We'll compile stand, let it do its work. And there you see it, slope for group 2. And sure enough, if it's in that model output, you can then use it in Bayes plot as well, like if you wanted to see the trace plot for it. If I just look at all the trace plots, oops, nope. This takes a second to compute. But you'll see right here, it shows up in the output with all the other markup chains, the category plots. And there it is. Questions?
In this case, it changed all the others?
It did not change any of the others. And so that's the key. Generated quantities happens after sampling is done and does not affect your model.
But in the model summary, I believe the betas are different.
They're slightly different.
Okay.
And that came from not running a long enough chain. I think it was 2.02 in the first example and 2.11 here. I actually just noticed my prior. I had specified my prior to have a variance of 1 for the intercept for some reason. I forgot to change that. That could also have done it. But they'll be roughly the same because it's not affecting the model. There is another section of stand code where you can put constraints in that will affect the model, or transformations that will affect the model. But generated quantities is something that happens after sampling is done. So whatever you specify in model and whatever you specify in generated quantities, independent. Okay? Sorry for the sloppiness in the code. Okay. All right. So, other questions on this, because we're about to buckle up, kids. We're about to take a ride on the matrix roller coaster. Here we go. Because we can make this easy also. Remember GLHT? What was the input to that function? Do you remember?
0 and 1.
Zeros and ones, a matrix that said put coefficients to multiply, put numbers to multiply the regression coefficients to add them together. We're going to build that ourselves. Behold, you may have heard of it before, a contrast matrix. I know when I hear that, I still get cringes from when I was in grad school in linear models world. God, quit telling me about contrast. I hate it. Especially polynomial ones. I don't want to hear about it. But this is trying to make your life easier. If we formed a contrast matrix, so this is a matrix right here. This is a matrix that has 1 row and 6 columns. Right? If we multiply this by our column vector of coefficients, remember, beta 0, beta 1, beta 2, beta 3, the values where 1 would take the betas and sum them together. So in this case, beta 2, beta 5, resulting in the sum that we're after. So it turns out you could hack Stan to take a contrast matrix every time and to ask for all these linear combinations to be computed within that matrix as you go forward. Because the product, contrast matrix times beta, results in the new linear combinations of your parameters. Okay? So remember, this contrast matrix here is size 1 by 6. Beta is 6 by 1. So the size of the result of this is 1 by 1. Right? Let's say you were really enterprising and you had 15 contrasts, it would be 15 by 6 times the 6 by 1, which would give you 15 by 1, or each one of those numbers would be the statistic you're after.
So you put all constraints and the same matrix?
All contrasts in the matrix, that's right. If we call this constraints, it means something very different. I don't want to correct your language, but this is one of those cases where it means a very big difference. This is called a contrast, which basically says, the language of that comes from like, almost like ANOVA back in the 1920s or 1930s, right? We want to do something with this, each of these, basically we're forming a linear combination of the parameters, right? Because the numbers we put in each of the columns will multiply that respective parameter in the beta vector. So here, with a 1 here and a 1 there, we get, okay. The other thing you can do with this, if you want to come up with a posterior distribution of a predicted value, right? You could plug in the values you wanted to predict with. I want the predicted value of somebody's in group 2 with a height of, 72 inches, right? So now group 2, 72 inches, you can intercept, because everybody gets an intercept. You put 72 right here, right? You would put, group 2 would be a 1, and then this value would be 72 as well, group 2 times 1. And you get a posterior distribution for a predicted value if you want. So you could talk about, for instance, you could use this same contrast to come about giving you posterior distributions of predictions. You remember in linear models, the prediction interval? Like we had this, do you vaguely remember that? We had like confidence intervals around predictions and confidence intervals around means and stuff. That's what this does as well too. For every value you put in, you can get a value out that makes your prediction and tells you the certainty with which that prediction is made based on the posterior distributions of your model. All right? Here, shall I show you? All right, let's build the matrix first. So the contrast is saying we have to, what we're really after is inputting this contrast matrix. So I'm going to define an integer saying how many contrasts we're making. In our case, that last slide had 1. I'll expand that in just a moment. So now we define a matrix that has number of rows equal to the number of contrasts, and number of columns equal to the number of coefficients we have in our beta vector, right? The number of columns in our X matrix. And then in generated quantities, I define a vector to contain the output of the contrast. Right? That vector is going to take the sum generated by this matrix product and store it for us. It's the same size as the number of contrasts we have, right? This is n times p. Remember, it's going to multiply a p times 1 vector. So the result will be an n times 1 vector, or n contrast times p by p times an n or p by 1 gives us n contrast by 1 vector. And where does it come from? That contrast itself is equal to the contrast matrix times beta. Right? Just like x times beta before, contrast matrix times beta. So if you're in a situation where you want to make a bunch of predicted values, you could use this. You want to make a bunch of inferences about some of the parameters, you can use this. Any questions? By the way, I love this type of thing. You know why? One of my hobbies when I was a kid, by kid I mean like in my 20s, I used to love predicting sports outcomes. I don't have enough time right now. I was going to do that running in this class. I was going to tell you, what's the predicted score for Iowa versus Michigan tomorrow? Right? What's Iowa's score? What's Michigan's score? I could do that. In the Bayes sense, it'd be nice to have a nice posterior distribution that reflected that score too. And if I had a linear model helping me predict it, I'd use this to come up with the scores. Or,
Aren't you being very humble about what you did? Because you were like featured on ESPN or something. I'm just saying. You're being
I was a really big
humble.
deal in Kansas City one year. Yeah, I had
Just throwing that out there.
It was like when you were at Kansas. I did this location and scale model.
Doing it, and then I saw the big blow up when you.
Yeah, I did a location scale model predicting NCAA tournament outcomes. I'll tell you more about that, the location scale part later. And it was using Bayes. I didn't use Stan. I hard-coded it myself in Fortran, which is a nightmare. But it basically ran on the same idea. And then, so if I have a posterior distribution for score 1 and score 2, if I really want to know who's going to win the game, that's just score 1 minus score 2. And I could form a posterior distribution for that. Now, if you're a gambler, that would be really important because that'll tell you the likelihood you're going to win on a bet you make. But yes, I did this for basketball. I was at a basketball school, KU. KU was ranked number 1 at the time going into the tournament. And KU had, let's say, a little bit of legal problems with their team. And so it was like their news organization. I tweeted something. Someone found it out. Can we amplify this? So the KU News made a story about it, sent it around to the local stations. And I was on like several of the Kansas City TV stations. Yeah, I was big in Kansas City. Which, yeah, not big, no. But it was fun.
I think it was ESPN. I don't think it was just
Really?
Kansas.
I don't know about that. Anyway, yeah.
I don't know.
It did pretty well. I mean, like it got like 78% of the games like correctly predicted. So I was happy with that. But anyway, so let's do this real quick. Here's the code for it. Oops, nope. That's not it.
So can I ask?
Yes, please ask.
So the contrast matrix that we're putting in is when you're adding interaction effects?
Well, we use it for many things. We could use it for predicted values. We could use it for linear combinations of model parameters. And because, for instance, in your homework, you have a question about what's the slope for whatever group it is. This math right here, because it's a sum of 2 parameters, that's a linear combination. There's no multiplication going on. And so this fits into that contrast matrix as well. So when you want to take some linear combination of parameters, be that for prediction or be that for inference of the parameters themselves, this is creating a new slope, for instance, right?
Yeah.
You use the contrast matrix. When you want a nonlinear combination, you can still use generated quantities, just not for, you have to make it up yourself a little bit differently. It's not as general. All right. Let's go here. I keep showing you. R squared is next, folks, I promise. Here it is. So what does my contrast matrix look like? I'm actually creating 2 contrasts in this example in my code. I'm creating one that gives me the slope for group 2, and I'm creating the other that's the intercept for group 2. Remember I had in the calculation and the math on my slide, I had what the intercept would be as well too? I'll do that. Does anybody want to see a prediction while I'm at it? I can just add another row to it. All right. Let's make 3 contrasts. The prediction's a little bit different. If you want to predict values, you have to sort of specify all the terms in it, including the intercept. So we need to put a 1 for the intercept, which is in row 3, column 1. How tall do you want our person to be that we're predicting? What's their height?
5.5 feet.
5.5 feet would be what? 60?
No, 66.
66 inches. Which diet group would they be in?
3.
Diet group 3. Okay, so that means group 2 variable is 0. The group 3 variable is 1.
You're essentially specifying the values.
That would multiply, like we have a brand new predictor. The group 2 by height would be 0, and the last value would be 66, which is the group 3 times height there. So this is 1 times 66. So if I do all that, and I build my stand model. Now, when you have the contrast matrix built in, again, you could just rerun the model with different contrasts, and it will output it for you. Run my analysis. Uh-oh. Something didn't work out. Oh, this is where I changed my code at first. Darn it, this is where I was trying to show you the matrix size, and it didn't work. Now let me recalibrate. And there we have it. This last value, we think somebody who's 6 foot 6 inches in group 3 is going to be 441 pounds. Wait, it's wrong. You know why? We centered it. Boom.
We should have 6, right?
It should just be 6. That's somebody who's 126 inches. But guess what? I don't have to recompile the model. There it goes. 5 foot 6, group 3, 248 pounds. I don't know. There you have it. So what does this tell us? This is the slope. This is our first contrast, the slope for group 2. And again, just like, remember how we talked about all the different effects of describing the parameters, right? What do we talk? EAP, which is the mean, standard deviation, highest density posterior interval or credible interval, right? All that applies in how to describe it. This is just forming it. So 2.08. 124 is the intercept for the group 2 slope, for the group 2 line. So somebody who's at 60 inches. So this is group 3, right? Group 3. Somebody who's in, I don't know. Am I getting that wrong? This is the group 2 intercept, pardon me. This is the group 2 intercept. So somebody who's at 60 inches tall in group 2 is this way. Our prediction was somebody who's in group 3, 66 inches tall. But again, you get a sense for what you think the range of prediction is. So if you really want to take a guess, you say, oh, I'm 90% confident their weight's somewhere between 243 and 253 in pounds. So, questions on this?
Can you show the code that you built for the contrast 2 and 3?
Yeah. The matrix, this
Yes,
code right here?
exactly, thank you.
Yeah, let me just display the matrix itself. Oops, I just zeroed it out. That doesn't help.
So line 305 is
The empty matrix. That's the right
you're
size.
essentially building a shell?
That's right.
Okay, and then 306 is,
Saying that, so this is for the very first row, the second position, the second column, and the fifth column are both a 1. And I shortened the syntax because you can do a double.
okay. So like, I'm gonna translate it to stable language,
Yeah.
because that's what I know. 305 is like generate, 306 is like replace,
Uh-huh.
307 is replace.
Sure.
And then like the 308 through 313 is replace specific values of the third matrix.
You can't know less about Stata than me, but I'll take your word for it.
Okay, thank you.
I'm serious. I don't know Stata. I've been able to literally open the program once or twice. That's about it. Yeah.
So I understand maybe you don't. I don't 306 and 307. I understand you're changing it to ones, but I'm not quite sure what you're doing.
I did a shorthand trick. I could have just done this.
That's fine, but I don't know why you're changing it to ones. I don't know what it's doing.
Oh, okay, so what you have to remember is if I do this here, if I did this, it might become more clear. These are the names of the betas, the numbers you're going to multiply.
Okay.
So here, a 1 for the 60-inch height slope, and a 1 for the group 2 by height slope interaction. Those were
So
the
2
two.
and 5 because that was the slopes for diet group 2.
That's right. Likewise, 1 for the intercept and 1 for the main effect of diet group 2 would give us the intercepts
Okay.
for slope for group 2.
Okay, I see the one.
And when Nikki said we want a 66-inch person in group 3 to predict their weight, we would put a 1 here for the intercept. Prediction, when you do prediction, you need the intercept. So we put the intercept back. The value 6 there is because remember, this is a height minus 60. And then group 3 is a 1, so group 2 is a 0. The interaction with group 2 is a 0, right? It's the product of these two. And then this last one is the product of these two. How's it going? Yeah.
Can you go back to that output for a moment?
Yeah.
please?
I'll try. This right here. Okay.
Okay, so I understand, okay, so you have these contrasts, right?
Uh-huh.
Slope, intercept, and so what are the outputs like beta 2, the mean and standard deviation? That's for
This is telling you.
height.
Yeah.
What does that tell? Yeah,
So these right here.
yeah,
This is describing the shape of that posterior distribution.
Okay.
So if I were to, let's see if I can grab my code real quick. Actually, I'll do this one. It's down here. So this is the slope for group 2 right here. The output that you saw in Stan is characterizing it with the very first contrast. So the mean of this is 2.08.
Yeah.
The standard deviation, which is sort of the measure of spread of it, is this third column. Sorry, you can't see that. 0.484. And then between 1.29 and 2.88 lies 90% of the distribution. So all the numbers that you see in the Stan output are summarizing the pile of draws that we sampled from the markup chain.
So we're combining to get that slope, we combined beta 1 with, beta 2 with beta 5.
That's right. That's right. And in fact, if you add them together, what you'll see is the mean of 2.08 actually comes from adding these two together. That is 2.08.
So we're adding together the slope of the height on its own with the slope of the height of the interaction with that group.
That's right.
Okay.
And why we did that specific combination was when we said, what's the slope for group 2? We started off, that kind of kicked off us plugging in some numbers. We start with our line, we condition on group 2, we have combined like terms, and this is our recipe for which goes what the numbers show up as. Okay? Thank you for the question. It's a complex concept, yes.
When we're doing the prediction
Mhm.
contrasts,
Yes.
in Bayes, do we report the uncertainty there?
Yeah.
Yeah, okay.
Absolutely. It's especially important. So a lot of times, when I see a lot of Bayes in practice, it's less about like the paper. It's more about like what's going to happen in this sporting event for me, or political outcome, or something like that. And you'll start to see you start to see that uncertainty get represented. It's represented in different ways. Depending on the site you're looking at. But yes, that uncertainty around the prediction is important. It tells you how much you should believe the prediction. I hate to sort of mention the hurricane that hit Florida this week. That cone of uncertainty, like where the hurricane is traveling. That's effectively what we're doing with the posterior distribution in prediction. This is our, This is our cone of uncertainty as to what the slope should be for somebody. Or if this were the third contrast, as to what the weight for somebody should be. So it is important. It's a really important concept. And just like in other linear regression, remember where in linear regression, do you remember where you had the most precise prediction in a regression line?
In the middle of the data, right?
In the mean of x and mean of y, if you had a simple linear regression, right? Same thing happens here. If you were to compare someone who was at the mean versus someone at the tail, the posteriors would be different. You want to see that or not? Take my word for it.
I just want to make sure we get to R squared because it's in the homework, right?
Okay. Let's do R squared. R squared is in the homework.
I'll try to keep my questions to finish them.
All right. Everybody ready for R squared? Behold, R squared. Let's go back to the basic principle. By the way, I had to look this up. It's been a while since I did R squared by hand. Remember, generated quantities, effectively, you're telling Stan what to calculate. And here's an R squared formula. You remember something called the regression sums of squares?
Sure.
Sure. Y minus its predicted value squared is what that is. Total sums of squares is y minus its mean squared, right? R squared is 1 minus the ratio of regression sums of squares to total sums of squares. So what we need to do is form all of this in Stan and have it calculate at every step of the chain R squared. Yes.
Oh.
Okay? So it turns out, what is the regression? What is y hat? Y hat is x times beta in matrices. Our model predictor matrix times our current values of coefficients. Okay? Y bar is sum of y over n. Now, r squared's a little unique because technically speaking, we're putting a constant in for the mean where we have uncertainty to it. But if we actually Bayes this up and allow this to be something variable, our r squared could be bigger than 1, and I don't want to do that. So we're just going to make it simple. Real simple. Took us a long time to get to. So we're going to have a mean of y. So let's do this. In generated quantities, if you put brackets around, anything you define in these brackets will not get reported in your output. So if you have these intermediate steps for calculation, and you don't want to see them in the output, you don't want to hold on to those chains for them because size or something is a problem, you put them in brackets. Okay?
Quick clarification,
Yeah.
sorry. It still runs it just doesn't like display the output?
That's right, it doesn't save it. So,
How quiet can it say that?
okay, well, so here, this r squared is 1 minus regression sums of squares over total sums of squares, where regression sums of squares and total sums of squares are defined or declared variables as real numbers. Anything in the brackets, now what we need to calculate that. For regression sums of squares, we need y minus the predictor squared, the sum of that. Turns out there's a function called dot self. In matrix algebra, there's a thing called a dot product. Just think of it as the sum of squared quantities for dot self. I could tell you more about it next week. So what we're doing is we take regression sums of squares here of y minus the prediction. What's the prediction? The prediction is x times beta. But because we're saving that prediction, we need to declare it as a vector. We know the size of that vector, right? X is n times p, beta is p times 1. So the result of this is n times 1, so that's a vector of size n. So we've got predictor. We take our predicted values, x beta, right there. We then calculate the regression sums of squares. We calculate the total sums of squares, where we take y minus the mean of y. Now, mean is a built-in stand function also. It just takes the simple arithmetic mean, just sum of y over n. And then at the output, you get this. And so, here's that in my syntax. Let's run this code. It's got to compile. This to me is the most fun example. I want to show you the trace plot of r squared. That is our r squared for each one of our chains. We just calculated the posterior distribution of r squared. Isn't that cool? Like r squared can now have a confidence one, a credible interval, a confidence interval around it. To me, that's really cool, right? Because we report r squared, but we never talk about our uncertainty with it in a lot of stuff that we do. Second, if we want to look at our output, actually, I want to show you the histogram with it. You see this is all bumping up against an upper limit here. I can show you the histogram of this. As you imagine, it's skewed. Right, it's not a symmetric distribution. So this is where a high density posterior interval will be a little bit different, right, than a credible interval. Right? Why is it different? Remember, highest density is the window that's the smallest x that contains that percentage of your credibility. Whereas the credible interval just takes like what you see in the output up here, starts at the 10th quantile and ends at the 90th quantile. Or, yeah, the other way around. I guess that's, yeah, never mind. Starts at the 5th quantile, ends at the 95th, excuse me. So what are we saying here? R squared, if I look at our summary again, our R squared, you actually have a posterior interval for regression sums of squares. And actually, you can even look at it, although I don't know why that matters, because it usually doesn't. You know, the total sums of squares is always constant. There's no standard deviation, no mean absolute deviation. That's because it's only, we're using, it's always the same. The mean of y is always the same, so that calculation is always the same. the R squared is down here. We think the middle 90% of it should be between 0.965 and 0.977. Now, this is a very narrow interval. But remember, these are simulated data, and we're bumping up against like perfect prediction. And for a normal R squared, you see this a lot lower, I think, and you see a little bit more range to it. It's Friday afternoon. Is your mind blown yet? Or just tired? Or both?
We can do both.
Now, I'll ask you, what do you think of this? To me, I'm like, woo, this is awesome. But what do you think?
I'm swinging back towards, yes, I'm understanding why Bayes would be advantageous. with all of this.
We can summarize uncertainty much more completely when we talk about an analysis. Now, that doesn't keep us away from the issue with, prior distributions being somewhat informative, but if we can talk about what we find afterwards, I think it can be very powerful. Other thoughts? What other questions on this? So with this, you should be able to complete your homework. And your code will look very similar to what I have, by the way. Yeah.
So R squared is telling us about the variance.
The proportion of variance accounted for by this expression.
Right. So this is very high.
Very high.
And
This is why I think this is fake data.
Gotcha.
Yep.
Okay.
If you had your real data and you saw this, people would get your autograph. Design an intervention.
Thank you, but your data is fake.
Oh, that's also true. It's also true. Very good. Now, I've never seen an R squared this high for most real data unless it's some type of like physical property, like, reflection of light or something like that, right? So, what else was I going to mention? So, where we're at, you literally, if you wanted to do your homework, could take that last stand syntax right here in this example and use it for your homework. Because it runs linear models generally speaking. If you use the model matrix, it will fit the right size. It'll calculate your R squared. And if you build a contrast matrix the right way, you'll answer every one of those problems. You'll have to run it twice because there's two models. There's one without interactions and one with interactions. But you could do that. So yeah, I know I put that in the middle of while you're doing your homework, but this is another way of looking. Yes?
So there is no non-matrix way right now that we know how to do R squared.
Right. You can figure it out if you want. You can put a loop in, but yes. Other questions? Let me think of it. Where else are we at? So this does all the linear models. Now there's two other parts of Bayesian analyses I want to talk about next week and then we're going to get into psychometrics. Those two parts. How do we tell a model fits the data in an absolute sense? And how do we compare two different models? So for instance, you pick your priors, I pick mine, which seems to fit better. We'll be talking about that next week if I can get my act together and build a lecture this weekend. All right, we're out of time. Thank you for being here on a Friday. Thank you to everybody online. I hope this is informative. You can tell I'm totally geeking out over it. I love seeing like the R squared distribution. Let that be your vision over the weekend, or not. Take care. Have a good weekend.